Very good afternoon. Now, in this particular part, I'm going to explain how to generate a stiffness matrix and what is the stiffness matrix method to analyze a structure. So this particular method, which is based on a matrix approach, by using this method, we can do the analysis of an indeterminate structure like a continuous beam, portal frames with and without sway, and like this. Now, first of all, so this is the first part. I will explain this particular topic in different parts. So in this particular part, I will explain the basics of the stiffness matrix. What is a term stiffness? First of all, we'll discuss on this. The definition of the stiffness is that this is a resistance to deformation. This is theoretical definition is it is a resistance to deformation. We say usually any element or a structure is very stiff. What it means? Very stiff in the sense the deformation, it offers more resistance to deformation, is said to be a stiffness. So resistance to deformation is a stiffness. So mathematically, stiffness is given by it is applied load divided by deformation, or in the other way, it is the force due to unit deformation. So here deformation applied is equals to 1. So due to unit deformation, what is the force generated in that element is the stiffness of that particular element. Now, what are the different types of the stiffnesses? So types of the stiffness, it depends on what are the types of the deformation. So for example, if a axial force is there, suppose there is a rod and it is subjected to axial force. It is subject to axial force. Then there will be axial deformation. So this axial deformation is given by, say, delta. So in this case, how much this force, axial force is required? So that this axial deformation will be equal to 1. Axial deformation equals to 1 is called as axial stiffness. Now, for this simple case, that is a rod subjected to the axial force. So deformation is given by the formula. Deformation is equals to PL upon A. So it is equals to PL upon A is the deformation, where A is the cross-sectional area, E is the moment of inertia, E is the modulus of elasticity, P is applied load, and L is length of the element. So, but by definition of the stiffness, so stiffness is given by P divided by delta. So from this equation, K will be equal to, that is stiffness will be equal to P divided by delta. So it is P divided by delta. So from this we get, so it is AE divided by L. AE divided by L. So therefore axial stiffness is given by the ratio AE divided by L. So that is stiffness of the element is always inversely proportional to the length of the element. So that is more length, then stiffness will be less. Also, it also directly proportional to cross-sectional area, and also it is directly proportional to the Young's modulus value. So this is called as the axial stiffness. So since the deformation is in the direction of axial force. Second type of the stiffness, that is, it is called as the flexural stiffness. So in the case of beam, which is a flexural element, so whenever it is subjected to any type of loading, then there will be a deformation. So this deformation is equals to, say, y. So this deformation y, or it is delta. Okay, now to produce this deformation equal to 1, this deformation is equals to 1. How much P force is required? This P force is required is the stiffness. So, and this stiffness is called as a flexural stiffness, is the second type. Third type, it is called as a lateral stiffness. So in this case, force applied is in the lateral direction. So for example, it is a portal frame and it is subjected to some lateral force direction. Then in this case, the deformation will be in the lateral direction. So this will be a lateral deformation, delta. Now to produce this lateral deformation is equals to 1. How much this P force is required? Is called as a lateral stiffness. And one more type of maybe there, it is there, that is a what is called as a torsional stiffness. So in the case of torsional stiffness, whatever the load applied is of a twisting moment. So that is, this particular rod is twisted. Now there will be deformation. So that deformation is measured in terms of angular deformation, that is in terms of theta. So to produce a unit deformation, to produce a unit angular deformation, how much twisting moment is required is the stiffness, and this stiffness is called as the torsional stiffness. So this is a basic concept of the stiffness. Now in the structural analysis, just we remember this formula, that is K equal to stiffness equal to P divided by delta. Now in the stiffness matrix method of analysis, it is required to generate three matrices. First of all, it is required to generate a stiffness matrix, then generate a load matrix, then generate a displacement matrix, delta matrix, and then relate this, that is combine these particular three matrices by using equilibrium equation. So we will get the unknown. So that is the stiffness matrix method of analysis. Next is whatever a stiffness matrix. Okay, the form of the matrix is something like this. A sample matrix is you are seeing here. These are the different elements. K stand for stiffness. So this location is K11. So that is a first row, first column. So this position is a third row, second column, K32. This position is a K13, that is first row, three column. So these are called as a elements of the stiffness matrix. These are called as the element of the stiffness matrix. And there are three rows and three columns. Therefore, size of the matrix is equals to 3 by 3. It is 3 by 3. Then in the stiffness matrix method, first of all, it is required to generate a stiffness matrix. But whatever the generated stiffness matrix is correct or incorrect, how to check this? Now there are three properties of the stiffness matrix. So therefore, generated stiffness matrix, you just compare with the properties, apply the properties. And if all properties satisfied, then it is said that generated stiffness matrix is correct. First property of the stiffness matrix is always it is a square matrix. Maybe 2 by 2, 3 by 3, 4 by 4, 5 by 5, but always it is a square matrix. Number of rows must be equal to number of columns. Then stiffness matrix is always a symmetric matrix. Okay, so symmetric matrix means element K21 always must be equal to K12. Then element 3,1 always must be equal to 1,3. Then 3,2 must be equal to 2,3. It is the meaning of symmetric matrix. Then, and third is element lying in the leading diagonals are always positive. Other elements may be negative, but leading diagonals means this. This is the leading diagonal. So element K11, K22, K33, K44, all the diagonal element must be positive. So these are the three properties of the stiffness matrix. Then the similar term that is exactly opposite to stiffness is a flexibility. Okay, now flexibility, this is the definition of the stiffness. So stiffness is what is the load required to produce a unit deformation. Load required to produce a unit deformation is a stiffness, while as the reciprocal of this is a flexibility. Okay, opposite to stiffer element is a more flexible. So it is delta divided by P. So what is the deformation due to unit load? Deformation due to unit load is called as a flexibility. So in the case of stiffness, delta value is equal to 1, deformation is 1, whereas in the case of flexibility, the load value is equal to 1. This is the basic difference. Okay, and suppose I will explain this flexibility in for one example. That is a simple case. It is a axial loading and it is subjected to axial load P. Then there will be a deformation. There will be axial deformation delta. Then what is the flexibility in this case? How we define a flexibility? That is deformation due to unit load. So that is this unit load, when the unit load is applied, what is the value of this deformation is the flexibility. Then what is the relation between stiffness matrix and flexibility matrix? That we'll see. See, this is called as a this is from the definition of the stiffness. So stiffness matrix will be equal to load matrix divided by displacement matrix. Then from this equation, the load matrix will be equal to K matrix into delta matrix. Call this equation number 1. Then what is definition of the flexibility matrix? Flexibility matrix will be equal to displacement matrix divided by load matrix. So which is equal to displacement matrix as it is. Now load matrix from equation 1 we can write as a K matrix into delta matrix. Now this delta matrix gets cancelled. So remain is only 1 upon K matrix. So therefore flexibility matrix is always the inverse of stiffness matrix or vice versa. So therefore once you generated the stiffness matrix, then find out the inverse of that matrix, you will get a flexibility matrix. This is the relation. Then second, one more important point is that what is a lateral stiffness of a column? What is the lateral stiffness of the column? So consider this column element. I'm calling, even though column usually it is vertical element, but here in the figure I have shown it horizontal. So consider only one, consider any horizontal element whose both ends are fixed, and here it is a lateral force is applied. Okay, or otherwise we'll consider the figure like this. This is a vertical element L. It is a column and it is subjected to lateral load in this direction. So when the lateral load is applied, so therefore the column will be deformed like this. Column will deform like this. So this deformation will be equal to a sway in the column, that is equals to delta. That is equals to delta. So in the case of stiffness, to produce this value equal to 1, that is lateral stiffness equal to 1, how much force is required is the stiffness, how much P force is required. Now whenever we apply some force here, then this end of the column remains at the same location, while as this end of the column will move by an amount equal to delta. Okay, so this becomes a level difference between the two ends, between the two supports. So this is displayed by delta. So whenever there is a displacement of where is the level difference between the two support, then the movement produced, that is called as a sinking moment. So the end which is displayed. Okay, so here which is at the lower end, here always the movement will be in the sagging nature. Movement produced will be always sagging nature, and this value will be equal to 6 EI delta upon L square. 6 EI delta upon L square, and it is anti-clockwise. So therefore here also at the other end also a anti-clockwise moment will develop, that is also equal to 6 EI delta upon L square. So this is a anti-clockwise sinking moment will be developed at the support, anti-clockwise. So this will balance by a clockwise couple. So clockwise couple means this must be, this force has to be act in this direction towards right, and this has to be act towards left. So this is a lever arm between this. So it is a resistive couple. This is a resistive couple having magnitude of both forces same, and lever arm will be equal to L. Then what is the value of these forces? Okay, so it is because of these movements. Why these particular forces were produced? Because of these movements. So these movements are both anti-clockwise in this particular case. So what is value? Always it is equal to M divided by L. This value is always equals to M divided by L. Values of the reaction. What is M? Is imbalance movement. So it is, what is this moment? It is 6 EI delta upon L square. Okay, anti-clockwise. And again, this is also in the same direction. So 6 EI, the 6 EI. So it will become say 12 EI. Just addition because the directions are same. So it is 12 EI delta upon L square is the value of M, imbalance moment, divided by L. So divided by L. So it becomes 12 EI delta upon L cube. So this value will be equal to 12 EI delta upon L cube, and this value again 12 EI delta upon L cube. But in the case of stiffness, delta value is equals to always 1. So what is the stiffness? 12 EI upon L cube. In the case of stiffness, It is 12 EI upon L cube. And if other word, if the question is that what is the stiffness of the column whose both ends are fixed? So what is answer? It is always equals to 12 EI delta upon L cube. 12 EI delta upon L cube is the stiffness of the column. Okay, and delta value in the case of stiffness analysis is always 1. So here also L is length of the column is coming in the denominator. So that means as the length of the column increases, it becomes more flexible or stiffness goes on reducing. So this is the first introduction part about the stiffness matrix, the stiffness term. Then in the next part, I will explain how to develop the stiffness matrix. Thank you.